Hello, so if you remember in the last video, I left you the open-ended question, which is, I want to try and find the best possible regression line, the best possible line of best fit that goes through my data. And I said, well, I know it's going to be a line, so it's going to follow the form y equals mx plus c. Now, just for reasons that will become a little bit clear, or will become a little bit clearer, one of the reasons behind doing a regression line and trying to come up with the equation of the regression line is that then we can estimate the value of data points which we don't currently have. So for instance, if you look at the data points which are on the screen, so I've gone out and collected data points from 4 people, I've collected their ages and I've collected their heights. But I've only collected data from a 3-year-old, a 10-year-old, a 25-year-old and a 30-year-old, right? That's the only data that I've collected. So in other words, if I wanted to, for example, go out and now say, I wonder what I expect the height of a 15-year-old to be, okay? Then I should be able to use my regression line to estimate what that height is going to be. And it should also be able to go backwards as well. In other words, if I give you a height of, I don't know, maybe about 200 centimeters, I should then be able to work out what the age of that person is going to be. So in other words, a really useful feature of the regression line is to estimate the value of data points without having to go out and collect them. Okay, so clearly it's going to be a regression line, so it's going to follow the form y equals mx plus c, where m is your gradient and c is your y-intercept. Now, just because I don't really want to confuse this with sort of coordinate geometry too much, so with sort of ordinary maths, I'm just going to call this y hat. So y hat because I'm estimating, okay? I want to estimate what the value of my data point is going to be, even if I haven't collected data on it, okay? So y hat is going to be my estimator. Okay, and I'm going to say that's going to be equal to, well, I'm not going to call it m for gradient, I'm going to call it b, okay? So I'm just literally changing the letters, why not? And then my y-intercept I'm just going to call a, okay? And just because I can, I'm going to flip the order around, so it's going to be a plus bx, okay? So what my job is literally to do, if I want to find the best possible regression line, in other words, the line that best fits the data which I have in front of me, I need to work out what's the best possible value of A and what's the best possible value of B. Now, in order to illustrate this, in order to understand the idea, I've got here a plot. So if you just focus yourself on the left screen for the time being, I've got myself a set of data, a scatter plot, okay? And you can see that along the x-axis, I've got my independent variable, and along the y-axis, I have my dependent variable. Now, what's good about this is that I can draw myself in a regression line. So let's just suppose I want to just sort of fiddle around with the regression line, so I can use these 2 handles here. And let's suppose that I think that maybe the best possible regression line, by the way, I don't think this is the best possible regression line, but let's suppose that I thought it looked something like that, just by eyeballing. So let's try and quantify this in a decent way. Well, let's first of all have a look at what we've got here. So just for the sake of simplicity, on the left side of it here, I've just basically drawn out 3 data points, okay? And I'm going to call them data point value of 1, 2, 3. So those are the values of my independent variables, just a case of simplicity. Okay, so what I've literally done here is I've come along and I've drawn myself a regression line, a line of best fit. And I know that this regression line is going to follow the form a plus bx, okay? So regression line, the estimator is going to follow a plus bx. But of course, I said the whole point of a regression line is that you should be able to use this to estimate data values. Now, the only issue with that is have a look. So have a look here at this value up here, okay? So this is the value, this is the data point which corresponds to the first data point in my data, okay? So in other words, if the x coordinate is 1, so the value of the independent variable is 1, then the value of the dependent variable is going to be like y. Okay, that's simply the height. That's simply whatever the value of the dependent variable is going to be. So this here would be my actual data value. Okay, so this is my actual data value, and it's got some height which I'm calling yi. Now the reason why I'm interested in the heights will become clear in just a second. But the issue is, if I come along and if I draw this regression line through my data, then it doesn't quite match up with where my actual data point is. Because I know that my actual data value is going to lie up here, but according to my regression line, for a value of 1, right, I know that my regression line says that my value should be down here, okay? my regression line is saying that my estimated value should be down here. So this here is my estimated value, according to my regression line. Okay, so this is my estimated value. So if you come back to the screen, I can draw my regression points on my estimated values on here. Okay, I can draw my estimated values on here. Now you can clearly see that there's some error which is going on here. You can see that there's some error. And the error is I'm basically saying that my actual data point should be up there, but my estimated data point is down here. So the error would be that much. Okay, the error would be that much. So that error, we give a special name. We call it a residual. So a residual is just simply the error between my actual data value and where I'm estimating my data value to be. So I'm going to call that distance R1. Now just have a think for a second, how do I work out the value of that residual? How do I work out how much error there is between my actual value and my estimated value? Okay, well I can do that just simply by subtracting my actual data value from my estimated data value. And of course, because I'm looking at the height, I'm going to be looking at the difference between the dependent variables. So where I'm saying my actual dependent variable value is and where I'm estimating my dependent variable value to be. So in other words, I can say that R, so any R, so for example, if I look at a different data point, this would be Y2, this would be the estimated data point, which would be Y hat 2, in which case this difference in here would be the residual R2. Okay, and likewise for the third one, this is my actual data value, Y3, this is my estimated data value, Y hat 3, and the residual would just simply be the difference between those two things. Okay, so in general, R of whatever data value you're looking at, so R1, R2, R3, in general Ri, okay, is just simply going to be given by looking at the difference between my actual data value, so Yi, take away my estimated data value. So that's going to be Y hat. I'm going to use that regression line to estimate that. Now what I can do, so if I look at those residuals, I can plot them on a new plot. So that's what I've got going on here on the right. So I've literally sort of said, I don't actually care about that straight line at all. All I care about is the distance. So if I replot those distances on a new plot, it would look something like this, which I've got over on the right. So clearly, what I'm trying to do to find the best possible line of best fit is to minimize those residuals. I want those residuals to be as small as possible. So at the moment, and I deliberately drew in a really rubbish line of best fit, a really rubbish regression line. So what I'm trying to do is fiddle around with different regression lines, and I'm trying to make these residuals smaller and smaller. So you can see here that that is a slightly better regression line because the residuals are smaller. That might be slightly better as well. So really it's a kind of optimization game. Clearly there's always going to be residuals, there's always going to be error, right? Because there's no perfect line of best fit. Unless your data is perfectly correlated, in other words, it all lies in a straight line, you're never going to get a line which fits every single data point. So the residuals are never going to be zero. But what you do want to do is try and make those error terms, try and make those residuals as small as you possibly can. So this is the aim. This is the aim when you're trying to draw the best possible regression line. You're trying to minimize those residuals. Okay, so in other words, you might have, at the moment, Y1 might have a value of, I don't know, about 3, and Y hat might have a value of, I don't know, maybe 1. Okay, in which case, the length of that residual, okay, the length of that residual in there, so R1, is going to be, well, 3 take away 1, which is 2, right? And likewise, you might have a look at the difference between the estimated value and the actual value of the second data point, which is going to look something like this. And I don't know, let's just say, for example, that, so R2 is going to be, I don't know, let's say it's going to be negative 1.5, okay? And let's say for the third data point, it's going to be slightly up here, it's going to be Y3. The value of that residual, let's say, is going to be about 1. Okay, so in other words, my three residuals which I've got here, R1 is equal to, what did I say? It was equal to 2. R2 is equal to negative 1.5. And R3 is equal to 1. Now what I want to try and do is minimize all of these residuals. So one way that I could do that is just simply by adding all of these residuals together. Okay, by summing all of the different possible residuals. So I take all of those individual residual values and I just simply add them all together. And what I want to try and do is make that sum as small as possible. Now there's an issue. There's a really big issue actually. If you have a look at this, so if I just treat this as it was, so if I just treat these residuals as they are, and if I just simply add together all of those residuals, watch what happens. So I get 2 plus negative 1.5 plus 1, okay? Well, when I add it all together, can you see that the negative values cancel with the positive values? Okay, the negative values cancel with the positive values, which is clearly not what I want. I don't want any kind of cancellation happening. So what I need to do is try and make these residuals all positive. Now the easiest and the simplest way of making residuals positive, in fact making any value positive, is simply just by squaring it. So I just simply take each value, each residual value, and I just square it. Okay, so I simply just square each value. So if I get 4 plus negative 1.5 squared is going to be, is it 2.25? Yep, absolutely, 2.25. Notice it's positive now. Okay, plus 1 squared, which is 1. You add them all together and you get yourself 7.25. Okay, so that at the moment for this data set here, so for the dummy data set that I drew down with 3 data points, not very good, but I got a squared error. So when I took all those residuals, squared them, then add them all together, I find it comes out as 7.25. My aim is to try and make that number there as close to 0 as I possibly can. In other words, to minimize the residuals. Minimize the residuals, okay? So we need to work out how we can do that. Now, fortunately, it's based around this. So just remember, how did I say, so I want to minimize this thing. So sum of Ri squared. Now just remember, what did I say? How did I say I worked out a residual? Well, I said I took my actual data value and took away my estimated data value. Okay, so in other words, this thing should be the same as the sum of my actual data value, so yi, take away my estimated data value, so y hat I, and then square that. Okay, so literally I've just said that Ri is equal to this, so therefore the sum of Ri squared should be equal to this as well. Okay, now just remember, I said that y hat I was equal to, y hat I is going to be equal to a plus b times my value of my independent variable, okay, at that particular data point, so xi, right? So in other words, I could replace in here the sum of yi, take away, and then I could replace y hat I with a plus b times by xi, all right? And then I've just got to square all that. And again, I could expand out that bracket in there so I don't have brackets within brackets, right? So therefore this could be the same as the sum of yi, take away a, minus b times xi, all squared, okay? So each of these 3 things here are equivalent ways of writing the sum of the squares of my residuals, okay? Now, by the way, just because you might come across this again, what I'm literally doing when I'm trying to make the regression line, so when I square the regression lines and add them all together, when I try and square the residuals and add them all together, what I'm literally saying here is I'm trying to come up with a least squares regression line. Okay, and you can see why it's called a least squares regression line. Okay, number 1, I'm looking at a regression line. Okay, number 2, I'm squaring all of my residuals. Okay, so I'm squaring in there. And what am I trying to do? I'm trying to make this value as small as possible I can. So I'm trying to make it small. Therefore, it's a least squares regression. So literally what I'm trying to do is take an equation that looks like this, and remember this formula because it is going to come in use later. What I'm literally doing is taking a formula like this, and I'm trying to make that value as small as I possibly can.